In this video, we're taking a look at data parallel programming with OpenMP. Data parallel programming is this idea that we don't want to explicitly manage our threads. Instead, we want to describe in what looks almost like a sequential program the opportunities for parallelism that exist in the data or in the way that we're processing our data. And then we let the compiler, perhaps some runtime systems, manage the actual execution in accordance with the available parallelism. So the programmer gets to express this parallelism in several different ways. The most important one, I guess the most popular one with OpenMP, is probably the parallel for loop. But there's also something called sections and something called tasks that you can use to express various opportunities for parallel execution. You don't actually tell it how to execute it. So the compiler is in charge of some of the nitty-gritties, like actually starting threads. We still need threads. They're there in the background. We just don't ever call, say, pthread create. Initializing locks, same thing. You do need to allocate and initialize your locks, but we could perhaps have the compiler manage that. In the case of a for loop, the compiler will divide up the for loop into suitable chunks of iterations, and then manage the distribution of these chunks to various threads for execution. So it looks something like this with OpenMP or data parallel programming in general. We probably have a master thread that sort of coordinates everything, and then at some point we enter a parallel phase. We perform some tasks for a while, and then probably there's a barrier. We wait for all those tasks to finish. The master thread might set up some new work to be done by multiple threads, and then that parallelizes out again, and so on. So the uses of OpenMP, it's in some ways similar to SIMD, but it's a lot more generalizable. So I suppose the most common application would be when you have a large array of values that you want to operate on in parallel. That's an excellent application for OpenMP, and oftentimes also a good application for vector processing, and the two are not exclusive. Every thread in OpenMP can certainly use vector instructions. So the two are complementary. But compared to vectorization, OpenMP has this, it's a little more general, I suppose. It'll work for any type of operations, whereas vectorization, of course, only works for vector instructions. On the other hand, it's only fast where the operations are properly independent. So if you do need to do a lot of synchronization, like you would if you were doing this in a normal pthreads program, then you will still need to do the same synchronization in OpenMP. It'll be just as fast, or just as slow, I should say. So there's no magic sauce here. OpenMP is a handy way of describing some classes of multi-threaded programs, primarily where we have like one workflow of things that sometimes can be split into multiple threads. If you have multiple threads that do independent things, or completely independent things, one is handling incoming connections and another one is handling some background processing, OpenMP is not the right task, not the right tool, I should say. So the primary advantage of OpenMP is the convenience. You can sometimes get a much more compact expression of the work you want done compared to a handwritten multi-threaded program. I suppose Sometimes there might be an advantage in having the compiler do the work, because the compiler might be better at parallelizing something than we are hand parallelizing, at least in the short term before we pick it up properly. But it's not. This is not a selling argument for OpenMP. And of course, OpenMP, it assumes that we have data dependence everywhere. If there are places where we have to have synchronization for correct execution, we have to put that in place. The compiler doesn't catch these things for us. There will be data races unless you force it to be synchronized, or perhaps you force it to operate on private variables and so on. Right, so one initial sort of design goal of OpenMP was that it should run on a single-threaded machine just as well as on a OpenMP like concurrent machine. And the end result is that all of OpenMP, it's not a change to the language, and it's also not a library. It's a set of what's called pragmas, compiler-specific directives that change the code under the covers. So it's not beautiful. It's not regular part of the language, and if you compile an OpenMP program without OpenMP, it'll still work the same way, and that's the advantage, or that was the goal of OpenMP. I don't know if it's an advantage really, but that was the goal. You should be able to compile it on any C compiler, but if your C compiler supports OpenMP, then it can run in parallel mode. This is probably, you could say that it's quite similar to vectorization as well. Vectorization works at a different level, but there, if you tell it that you have vector instructions, the compiler will vectorize, otherwise it won't, but the program will work the same. I guess the advantage of vectorization is that there you don't, as long as you're using the auto vectorizer, there you don't even see the changes to the program. On the other hand, you then get very little control over it too. Right, so the basics of OpenMP, how do we actually use it? Pretty straightforward, and we'll go through some examples next lecture. First, important to compile with -f OpenMP. That's what enables everything. For some things like these functions, you need to include omp.h, but for the pragmas, those are built into the compiler. They're not something that would be in a header file. So if you're not using these, you can get away without the OpenMP or OMP include. Okay, so there's all these directives, and there's more. Let's just briefly review what they're doing. So we have, for all the pragma OMP directives, it applies to the following statement or block. So it might be a function call, or it might be something in curly braces, or it just might be one operation. It doesn't work for declaring variables. It needs to be, so it's not statements, I guess. Expression, really. It's probably what it should say here. Okay, so to start running a bunch of things in parallel, you just say pragma omp parallel. Now it'll run on all the threads that you can tell it how many threads you want to have with an environment variable, or it'll just use all the cores on the machine by default. So now it'll run the remaining code in your program, the following block or the following expression in parallel. Okay, So that means if you just have a, say, a printf statement following after, you'll get many printfs, or many prints out of that. That's not necessarily what you want. Sometimes we want single-threaded control for a while and then spread it out to run some computation on many threads. So if you say within a parallel block, you say pragma omp master, now it'll only run following expression or block on the master thread. Similarly, single is very, very similar, but here it'll run only on any one core instead. Sometimes you're running in parallel, and then there's a part, a critical section, where you're modifying a shared variable, let's say, that you need to have a lock around. If you just say pragma critical, it'll acquire some global lock, a single global lock, before running the rest, or the following expression or block. Or if you give it a name like this, it'll acquire a lock called this instead, and you don't need to allocate the lock or initialize it. It'll just work behind the scenes. Right, these two functions are handy. Sometimes you want to manually split some work among all the threads. You can get your thread index or the number of threads available on the system. So with these pieces, we can build any concurrent program, really. But there are also some handy convenience features that make the program even more compact. The most popular and sort of the claim to fame of OpenMP is the OMP4. So if before a for statement you say pragma OMP4, now it knows that this coming for statement should be treated differently in particular, and this does need to run inside of a parallel block. In particular, it'll, for this for loop, then it'll chop it up into multiple little chunks. And that depends a little bit on settings, we'll see later. It'll chop it up into multiple little blocks, stick those blocks or tasks into one or more work queues, and then the worker threads will then automatically take elements out of the queues and do the prescribed work. So in very compact fashion, you could take a single-threaded for loop, add one of these statements to it, and now we'll run it on many cores. Of course, data races or data conflicts overall are not managed. So we need to do something about that, probably. If our for loop is about computing a sum of a bunch of elements, as it has been so often in this class, then the sum, as always, in this case, and also in this case, would be subject to a data race. We would be writing to the variable sum from several different threads at the same time, and we risk losing some of those updates. So one good way to address that is you can annotate things in the loop. So you can say like this, right? Pragma OMP4 private sum. So that means now that, just like it says here, the variable sum is private. It has a sort of a copy within. It creates a copy within the for loop that applies only to each chunk, or each chunk at a time. So in this little illustration here, we get perhaps 3 different chunks, each with 4 iterations in it, and we'll have a separate sum for each one of these chunks that we can compute. And that's only available inside of the block now. If you want to have the sum outside of the block, we need to somehow combine all those little sums into one big sum, and that's called a reduction. So then we can tell it, that, to compute the final sum, we should use the operator plus on the private variable sum, and then we'll be good to go. So if you say like this, now it'll automatically make sum private, and then at the end of the loop, after the implicit barrier here, it'll one way or another safely reduce all those little sums into one global sum, and that's what's available after the loop. And finally, there's this schedule where you can tell the compiler how big a chunk should be. You can tell it a strategy for how the various cores should decide what to do next. If you go with static, then every core, I believe, would get its own queue, and the chunks would be split among the queues, and then when a queue is empty, that core stops working and just waits for everyone else to finish. Or you might have a dynamic strategy where we have the still a fixed chunk size, but a single queue. So now all the cores take from the same queue, which means when the queue is empty, everyone is done. So I suppose that more efficiently uses the cores. On the other hand, we have a shared queue, which you have to have mutual exclusion on, so that can slow things down. There are several other approaches too. They're mostly dealing with the chunk size. Maybe we don't want a fixed chunk size, we want to vary the chunk size depending on how quick things are going, things like that. Okay, so that's four loops. Chop it up into little chunks. If you don't know how long the for loop will be, like you don't have a good end condition, so it can't count the number of iterations, that severely limits how much OMP4 can do. There may be some things it can do, but I think for a static schedule, probably not. We'll have to experiment with that in class. Okay, so another alternative, well, sometimes we don't have for loops, but we still want to parallelize something. It might be that within a function, there are several things that we do, and each one of those things can be run in parallel. And that's what sections are for. So now we can tell the compiler that we have a series of sections coming up. Each one of those can run on a different core. So here it'll actually cut up the this sections segment, sections block, into multiple tasks, and each one of these internal sections here will be added to a work queue, and then those will execute on whichever core is available. And then finally, there's something called tasks, which is, I would say, quite similar to sections, but a little more general. So in tasks, you can say the following thing, the following expression or block is a task on its own, added to the queue, and you can do that anywhere you want. So sort of a common design is we have first a single-threaded execution that generates a bunch of tasks. Here's a very basic example. Now we're making 10 tasks. And each of these tasks will then run in parallel. They would all call something parallel here, independently, running on 10 different cores. Right, so here this pragma-omp single is running on one core, and then as new tasks become available, the other cores will pick those up and start running them. And here it might be convenient then to wait with a pragma-omp barrier or a task wait after, let's see, probably after here. Perhaps this something parallel actually needs to be finished, say we're initializing a large array, we'll put a little barrier after, and then we can go ahead and do the next phase of the computation, issue some more tasks. Right, so that's pretty much all there is to OpenMP. It's not a very complex standard. It's not a very beautiful tool. It also isn't particularly powerful, but it is very convenient. If you write a sequential program, you might even be able to, you might have a domain scientist write the sequential program, because they can do some of it. And then it would be relatively easy for someone with a little bit more know-how in concurrent execution to just tack on some pragmas and make it run parallel and a lot faster. There are some other tools for running OpenMP programs across multiple machines in distributed fashion and so on. They're less popular. There are other ways to do distributed computing, and we won't look at that, at least, yeah, not in this class. But yeah, the main application for OpenMP is just multi-core execution. Of course, you can't expect anything to go much faster than the number of cores you have. So if you have a 16-core machine, just like with pthreads multi-threading, you can hope to get 16 times faster. Probably you won't quite get there due to cache line conflicts and all the other problems that normal multi-threaded programs encounter. That's all I have. I'll see you later.